Hello, my name is Nathaniel Madrigal, and I'll be doing a code review on Code 3, which is Uniform Random Query Sampling using Multidimensional Range Tree. So the main purpose of this code was to make a multi-dimensional range tree, or implement a multi-dimensional range tree. Because in Code 1, if you need a review, implemented a one-dimensional range tree. This one want to make it so it could be any dimension higher than 1. And again, it will return it uniformly at random. So here we have a max dimension equals 3. This is important. This says how much dimensions is going to be set for. And this scenario, in this test we just did 3, but they could be any number higher, like 3, 4, 5, etc. So how we did this is that each point has to contain the values for every dimension. So let's say the first dimension is the x, second dimension is y, and the third dimension is z. You have to have a coordinate on the x, y, and z. So here we have an array of values. So for every dimension, we say the d minus 1 index contains it. So for the x, it'll be on index 0. For the y, it'll be on index 1. Z index 2. So that's how we do it. And then same thing, left, right, the pointers to the nodes, the weight, and then t associated. This part is important because this will be actually what allows you to do multi-dimensions, but we'll go over that later. So here we have a range, it's just a min-max for one dimension, but a query range, we say, is an array of ranges. So it's the same thing as the values of the nodes. The indexing is the same for each dimension. So index 0, you have the range for the x, index y, or index 1 will have the range for the y, on and so forth. And then here we have partition sort nodes. This is just a quicksort implementation of sorting nodes. And this just so you could say on dimension D, I want to sort it based off of that. So I wanted to say I want to sort the nodes in the x dimension, give it 1, it would sort on x. Sort on z dimension, I'd give it 3, it would sort on that. And here it gets like the get val d, so it knows the values and whatnot. Okay, now we're going to be going the actual functions on the range tree. So this is building the range tree. So here we said it starts as a P list of nodes. D starting dimension always starts at 1. So when you're building the range tree, you're always going to start at 1. And then if it was like code 1, it would just be like this. But we see that the first thing we do is build an associated tree based on a higher dimension. So here we have a list of nodes. And so the entire list, and we're going to build a range tree based off that. But every node will also contain a pointer to a built range tree on a higher dimension, but it's same P, but it's going to be sorted on a different dimension. It's going to be sorted on the higher dimension. So if we first sort on X, it will now sort on Y. And then Y will then contain a pointer to a range tree sorted on Z. So every node, like I said, will contain a T associated, as you see. It will build the T associated in the beginning, and then it will make sure to assign the nodes T associated, that's the name of the variable, to the actual root of the range tree. And then here, make just so that if it's higher than the max dimension, we want to stop building associated structures, because let's say if you have only 3 dimensions, when you don't want it, you can't build anything on 4 or 5, etc. So here is where we get a much higher space complexity than the one-dimensional case, because you're going to have to store the space of all these associated structures. Find split node, very similar to the one-dimensional case, the only difference being the D again. And then here, normally where we'd compare, let's say if the x is greater than the x max, we do get val d and then get range d. That way, so it can change. So you can you could find a split node of a range tree based off of X, or you want to find out Y, and then because you want to search the associated structure you built over here on a higher dimension, but to do that you're going to have to find the split node on a higher dimension. So that's why we have the D. Find canonical set. Okay, so this is where the magic happens. You always again start the build starting dimension always starts at 1, so D will always start at 1. And then it's going to do this is right here is exactly the same or very similar to the one-dimensional case. The difference being that again, instead of we say x is greater than x min, in this case we do get val d, get range d. But the concept is the same. So the way that we're going to split up our search into each dimension. So the cube will contain all the ranges. So it'll contain the ranges for x, ranges for y, ranges for z. But at first, we're only going to care about the x dimension. So it's going to find all the canonical nodes using the logic explained in 1. It's going to find all the canonical nodes for the x. But then now, for every canonical node on the x, we're going to search its associated structure. And then you'll see that being done in this code right here, this small snippet right here. So just how this works, if the D is equal to max dimension or you have an empty list. So C will contain at the end, because you're appending all the canonical nodes, it was a list that contains all the canonical nodes on D dimension D. So if that's empty, return, and if it's it's equal to max dimension, you can stop. But other than that, we have this thing called a sum. So this is going to be the sum of all the lists on the associated structures. So let's say in this scenario we're on dimension 1, and then now we're going to add, the sum will be, it will add all the lists on the Y. So here you see, so it's going to search through every canonical node on let's say 1. It's going to check if the pointer to the associated structure is actually viable, and if it's none, it's going to check the next one. And if the pointer to the associated structure is not none, and you can actually search it, it's going to find the list on the Y. So like if we say we're on 1 in this scenario, so it's going to put in the root of associated structure of the associated structure, and then it's going to find this smaller list where it's going to be sorted on, you already found on X, and this is going to find it on Y now. And then it's going to, if there's actually nodes in this list, it's going to add all of the associated lists into this sum, and it's going to do this for every canonical node. So it's going to sum up all the lists from the associated structures and then have it turn it in this one sum. And then this will let's say in this three-dimensional case, find all the canonical nodes of X, then search through every canonical node to find all the canonical nodes in Y, then search those to find all the canonical nodes on Z. And then those ones on Z, those are the ones that are, let's say, the true canonical nodes, because it's they're perfectly sorted on X, Y, and Z. And this whole process is to add up those ones at the very end into one list that you're going to return into CSUM. And then uniform random node, it's like exactly the same as the first case, or the first code. It's just going to have, it's all the canonical nodes, you found them, so it's just going to do the same logic where you have the keys and whatnot, and it's going to find the max key and then traverse down a canonical node. So here it's going to see how we actually use the functions and whatnot to test it, or in an example. So here, right here, we're just building a database. This is building a database of nodes where it has random x, y, and z. Then here, we build a range tree based off of this because database is a list of nodes. And like I said, it starts at 1. Dimension always starts at 1 when you're doing a build or you're doing a find canonical set. We see here that we have 3 ranges, the x, y, and z range, 500, 1000, 400, 600, 750, 850. So those are just some arbitrary ranges we set. For example, query range is just a list of those 3 together. And then we're going to find the canonical nodes. We're going to find all the canonical nodes of this range tree and its associated structures. And then we're just going to return a random node from that list of canonical nodes. And then here we see an example. Our random node is 638, 561, 849, and that is in between the 3 ranges we set. And then here we have some tests. This code is just testing that it does actually work. So it's going to iterate it 2,000 times. And it's going to see all the points it returns. You'll see that we'll only get 1, 2, 3, 4, 5, 6, 7. 7 points actually fit the criteria of what we set. It's going to see how much times each one is returned in the 2,000 iterations, and we see that they are approximately uniform random. Then if you increase the amount of iterations, you would get closer to perfectly uniform random. So we can say that it is uniform random. And then we see the ranges, just the min-max on each one, that they are in between the ranges we defined. So the code is correct. Okay, that is it. So just slight alterations to code 1 to make it work in multi-dimensions. The big thing here is really just searching the associated structures and then adding back all the lists on the associated structures into one list that will then return.